Okay, great. Hi, everyone. Thanks for coming to the Grundfest lecture for this month. So the Grundfest lecture is named in honor of Professor Warren S. Grundfest, who was a professor of bioengineering, electrical engineering, and surgery at UCLA. And he was very much an advocate of junior scholars. So this lecture series is organized by Professor Kadambi, Professor Bauman, and myself. And we are grateful to Akasha Imaging for sponsoring this lecture series, which also has an inverse honorarium for non-permanent speakers, like PhD students and postdocs, for example. And today we're very excited to hear from Yash Kant, who's a PhD student at University of Toronto. He's going to talk to us today about making diffusion models 3D aware. Okay, go ahead, Yash.
Thank you, Katie, for the thank you, Bertie, for the introduction. I'll share my slides. I hope my slides are visible, and this is so. First of all, thank you so much. I'm Yash. I'm a third-year PhD student here at University of Toronto. Thanks for inviting me. Very honored to talk to you all about my research. And this talk will be about making 2D diffusion models 3D aware. So let's get started. Here's an overview slide of what I'll be talking about. I'll first talk about image generators, which are diffusion-based, and what is their working principle, the scale of the data that they're currently trained on, and how they are trained. From here, I'll also briefly mention the progression and the improvements that have occurred in them over time. And the main part of this talk will be about how can we make these models 3D aware. So this will probably take 25 minutes. I will talk about two of my works, which is SPAD and Imvs, and I will contextualize these works in the context of other works that have also existed in this space. After this, I'll conclude with some reflections and learnings that I have learned from these research. So let's talk about image generators. From 2014 to 2020, generative adversarial networks were a popular method of generating 2D images, as well as videos, and they had a very steady growth of different types of things we could do with them. However, GANs suffered from an issue called as mode collapse, where they were unable to fully represent all the training data uh, modes or categories that basically we wanted them to capture. So here's a small visualization of that. So this issue exists even on a tiny data set such as MNIST, which has images of digits from 0 to 9. And we can see that this particular GAN here is even unable to generate simple digits such as 2 and 3. So just out of 10 categories, it is missing digits such as 2, 3, and 8, and it is generating these digits 1, 7, and 9 very often. And all these samples were just randomly picked from the generations. So due to their lack of generalization, we moved away from GANs, and diffusion models arrived at the scene. They started taking off in late 2020s, and it was actually picked up by the community after this paper from OpenAI came up, which showed that they could surpass diffusion models could surpass GANs in terms of their image quality. And by the way, we had already over-engineered GANs up till this point, so replacing them was a difficult task. Diffusion models had a very slow growth in the beginning, and then they suddenly picked up once they were scaled and shown that they worked better. Something similar also happened in the context of vision transformers when they replaced convolutional networks. So let's talk about how diffusion models work. And here I have this slide where on the left hand side we have some training data which has these multiple modes or categories, and on the right hand side we have this prior or this noise distribution from where we sample. And we start with this training data set, and we basically want this noise to map to our training data set. And diffusion models allow us to sample from this prior normal distribution and iteratively denoise to match this training data. So more concretely, we define a forward process first, where we basically take a sample from our training data, and iteratively destroy the sample by adding Gaussian noise to it. This forward process does not use any neural network or have any learnable parameters. So after this,
Oh, did we lose Yash?
It looks like it. Huh.
Hopefully he knows.
Yeah, maybe I'll send him an email. Okay, I sent him
No
an
one has
email.
his phone number.
Hopefully he sees it.
No one has his phone number, right? Just
I sent a Slack message mostly.
Okay.
all right.
Okay.
Sorry about that. So let's go again. So I was talking about this forward process, which basically allows us to convert, to take a sample in our data and destroy it and map to a noise distribution, which is the prior distribution we have. After doing this, we define a way that we can actually sample from this noise distribution and get back to our training data, which is basically the generated process. And we define this reverse process that basically learns to iteratively map our prior distribution to our training data and allowing us to generate samples. Within this process, we basically learn this core function using a neural network. So this is where basically all our trainable parameters exist, this particular function here. And this is defined as the gradient of log likelihood of our training data. And this is like a very high level overview of how like traditional diffusion model works. And these days, people have moved on from like using like the score matching. So this particular formulation is of using a score-based method, and folks have moved away from like score-based methods to something much cooler, which is like flow-based models. And they have like slightly smoother and better controllable trajectories over the space. So you can refer like to these two shared citations for like reading up on both of these things if you want more context. So modeling wise, like how do we model basically the score function? We use this denoising UNet. So UNet is basically a decon and a convolution and a deconvolution network, which basically produces the uh, a sample from the distribution, which is slightly less noisy than the one that we actually gave it to. And this allows us to basically go from noise to a training distribution. And another bit here that I missed to mention is that we can actually condition this UNet on a type of on any type of latent representation. In this case, we can condition it on a semantic map or a text or images or anything. And we have used this particular way of conditioning to basically enable us to generate images from text. So so using this particular thing, we were able to condition this diffusion model on text, and we basically scale them to internet level data. So we use this data set called as Lion, which has 5 billion samples of images and text. And we were basically able to generate these type of very high quality samples on the left-hand side that I showed. And this all happened due to Stable Diffusion. And since then, these diffusion models have kept improving and kept getting better and better and better. So they basically have become faster. Something called as distillation has worked out pretty well. And as DTervo has come out, they have become much bigger, which basically like we replaced the unit with a transformer and made the parameter count go up much higher. And they have also become more accurate. So these images are pretty impressive, and they are pretty good and 3D consistent. And they also have a very high level of articulation and detail. So a question that comes to your mind is like, if they understand this 3D world somehow, can we explicitly control their generations? Or their generations, or like basically, can we make them generate images that are that are of the same asset or of the same scene in different 3D viewpoints? And this is what basically my talk will be about, of how can we somehow control their generations in 3D. So here's like an overview of the things I'll cover in this particular space. So I'll talk first about the task and the data set. And then I will talk about like 4 different methods here. So the first one is 0, 1, 2, 3. This was like published in ICCV 23. Then 2 of my works, which was like INVs and SPAD, which were sequentially published as SIGGRAPH and CVPR. And between them, this MV Dream work, which has come out, which also provided us with a good baseline of how to do this. So let's talk about the task and data set that we use. So the task is simple. Given a single image of an object, we want to generate novel viewpoints. So for example, let's say given this object of this laptop on a stool, we want to generate it from 2 different viewpoints. So formally, we refer to the given image as source view and the novel views that we want to generate as target views. We specify these novel viewpoints using their camera poses. So basically, we use some rotation and translation between the source and the target camera to explicitly specify how we want to move the camera in the space. And the data set that we use is basically observers. It contains 800,000 3D assets from the internet, and we can render these assets from different viewpoints to generate the data for our task. So let's talk about our first work, or the baseline that we use. So this is 0, 1, 2, 3. This was published by folks from Columbia University. And I'll discuss the method of how it basically works. So we basically use the first source view, the first image that is given to us, which is this, and the relative transform between the source view and the target view as conditioning to our latent model. So a latent diffusion model, or the stable diffusion model. We push the source view through a clip encoder, and we use the relative camera pose, like this RNT, we encode it using a dense MLP conditioning. And then we train a stable diffusion model to denoise our novel view used on this data set. So since we know the ground truth, we can just create this as a loss. And here are some results that 0, 1, 2, 3 achieved. So it was able to achieve good results. Like you can see, it can synthesize, given this input view, a good generation of a novel viewpoint. But it suffers from some issues. So the first one is that it suffers from insufficient reuse of input pixels. For example, basically, sharp details such as text and texture get garbled. So you can see that given this image, this whey protein, you can see that it has some text on it. And that text gets garbled because we push this through a clip encoder.
I guess we lost him.
Yeah, looks like it.
Aviad, can you Slack message him again?
Yeah, I don't know that he's seen my first Slack message.
Oh, okay. I just thought it might be faster.
I'll send it.
I'll
There's
email
still
him again.
he's still on. I think he has 2 usernames.
Oh.
Hey guys, sorry. So coming back here, so we have this given image, and it has this sharp details of text and texture. And when we push it through a clip encoder, basically all of that gets garbled because we are pushing it through a dense network, and there is no way to basically recover those details once it has gone through that dense network. And 0, 1, 2, 3 basically garbles those, and we can see it here compared to the ground truth, which basically is a clear text. So cameras, and also the second issue here in 0, 1, 2, 3 is that the camera is encoded also in a dense vector, which does not allow for very good control because we are not specifying it explicitly. And then that ends up with basically these alignment issues of the generation is not aligned well with the orientation of the ground. And the last point is that the 3D consistency is not guaranteed because there is no explicit way or no explicit prior here that can push it towards 3D consistent outputs. So 0, 1, 2, 3 had few shortcomings, and we worked towards fixing these, or a few of these in our SIGGRAPH Asia paper that I will discuss next. So we adopted an alternate approach basically towards fixing these issues. And the name of the approach is Imvs, which briefly stands for In Painters for Novel View Synthesis. And this was a fun collaboration with folks at Snapchat and U of T. So the research question that we asked is like, can we reframe this novel view synthesis as an image completion task rather than generation from scratch? And we were inspired by these works from works such as Infinite Nature, where basically they generated views by completing, generated novel views by completing the first image and slowly transforming it into what comes next in the video. And we find that the answer to this question of like, can we reframe it is yes. And let's discuss how we basically can approach it in such a way. So we first create a partial view by reusing source image pixels. For this, we first use a monocular depth estimator, in this case, Zoe depth, to create a depth map. And then we reproject these. Basically, using this depth map, we can apply every pixel some depth, and we can project them in 3D points and create a partial view. So this is how that looks. So now that once we get these partial views, the task remains is that basically we want to take this partial view and just in-paint it to generate the final image. And for that, we use a Stable Diffusion in Painter. However, Stable Diffusion in Painter is trained to generate only 2D front-facing views, but we want to generate something that is consistent in all viewpoints on 3D. And for that, we basically train the in-painter on this observer data set to learn 3D completion priors. So we do this by also adding some more tricks, not just by learning it on the entire data set, but by being a little more clever about how we go for this. So the first thing is that we are given a source view, right? And we want to generate something that looks like a second view of this object. But we do not want to basically inpaint every single pixel, but we only want to inpaint things that are occluded in the first view. So for this, what we define is that we define an epipolar mask. And what it does is that it basically only highlights pixels that were occluded from the first view, so that we don't have to inpaint every single pixel in the new image. And for this, we use these epipolar lines that basically bound the generation. And this is like a visual of that, where these are the directions in which we only want to inpaint. And when we provide the in-painter network with an epipolar mask, its job gets much easier because it only has to constrainedly generate these particular regions. One more thing. So when we generate this epipolar mask, there is we use a soft valued mask from 0 to 1, because what happens is that if we basically move our camera 180 degree behind the object, then a lot of the pixels can get flipped. For example, here, we want to generate this object from almost an opposite viewpoint. And in this case, we want the in-painter to not just edit the new pixels, but also the pixels that were reprojected by a reprojection mask. And for this, we use the soft valued in-painting mask that tells basically what is the angle between a source view and the target view at every pixel. And that is why this mask is smooth, and it has this small gradient, which basically shows the angles at every pixel. So using these tricks and these in-painting masks, we basically train our network. We fine-tune our Stable Diffusion on 96 A100 GPUs for 2 weeks. We use 20 million observers rendered images for this and fine-tune our network. There are 2 more tricks that we use here. The first one is that we notice that the object boundary of our generation appears as early as the first 10% of our denoising steps. So we just sample these steps with a slight bias towards early steps in our training method. So this is an example of it, where basically we see that in 10% of the steps, we can see this share emerging. And in 50%, it is almost as good. So only initial few steps are used for this generation. And here are some qualitative results from our method. Because we explicitly transfer the source pixels to the target view, compared to 0, 1, 2, 3, we are able to preserve these text and textures much better. So you can see these words whey protein still exist in the final view. And similarly, like you can see again that Imvs is able to preserve the structural and semantic details much better. So this toaster here that looks like that has these toaster slots becomes a grill when generated with 0, 1, 2, 3. But our method is able to preserve these things intact. Another good thing about using in painting is that we can actually now in paint without being constrained with image resolution, without being constrained with like a particular original image resolution. We can use multiple views and splat different things into a 3D point cloud and then create a final image. So our resolution is also much higher. Like we can work at 512 cross 512, which is almost 4 times higher than our baseline. Let's jump into some quantitative results. So numbers wise, we also outperform 0, 1, 2, 3 on 2 out of the 3 metrics. So we are better in the PSNR. We are also better in LPIPs, which is perceptual similarity. We do have a shortcoming here, which is in our structural similarity metrics. And I'll briefly discuss after this why that happens. And we show this on 2 different data sets. So GSO is a synthetic data set of synthetic assets. And the second one is Co3D, which are human captured objects or videos. So why do we basically struggle with the structural similarity index, right? The most important failure mode that we notice is imprecise depth. Since we take this source view and we apply depth to it and project it, a lot of the times this depth is basically noisy. And when it is noisy, the unprojected view, the partial view that we generate in itself becomes noisy. So for example, this cap here, once we apply depth and create a partial view out of it, we can see that basically all the edges are destroyed, right? Like these are deformed. And now if the in-painting network gets this as input, then the generation of this in-painting network is not going to be as great because it basically has to fix these edges. It has to smoothen out these edges. And this is one of the most common and recurring failure mode in our setup. The second failure mode that we suffer from is some downsampling. So this takes place because of the latent diffusion model. We take our image, we compress it down to a much smaller resolution of 64 cross 64. This is an artifact of the method that we use, which is stable diffusion. And this accompanied with poor depth projection leads to basically these type of deformed partial views and some holes blending into our texture. And the third one is like when there is large viewpoint changes, if I'm taking an object from the front facing view and I'm flipping it towards the back of it, then some of the texture gets reflected back at us because because in this case, it's very hard to say what is behind this object. And when we create a partial view, it is going to look something like this because it's basically flipped. And due to this, it throws off the in-painting network, and it may fail to detect that basically it has changed by a large margin, and it just tries to complete this partial image, and which leads to some flipped view problems. So we explored INVs in 0, 1, 2, 3, and we found that they suffer from these different set of issues when generating novel views. Now I will cover a couple of alternate methods along similar lines that have tried to make different types of approaches, that have taken different types of approaches to address the same problems. So another one I'll talk about, this next method is MV Dream. This is a work from ByteDance. The task here is slightly different. The task is that given a text prompt, we want to generate 4 consistent and orthogonal views. So basically, I don't want to take first image and generate a second view from it, but I just want 4 views of the same object given some text. And here are some samples of that. So an astronaut riding a horse, and here are the 4 views that we want to generate out when given such text prompt. So the method is somewhat similar. We basically train a stable diffusion to generate 4 orthogonal views. And these are the 4 views here, like 4 orthogonal rendered views. And we apply some text conditioning similar to similar to stable diffusion, but with that, we also merge in the camera viewpoints that we want to generate. And that is very similar to 0, 1 to 3. Now, the only catch here is basically how do we enable communication between multiple views? And the answer to that is just by extending our self-attention. So on the top here is an example of a single image diffusion model where each pixel in the image looks at each other, this place. And at the bottom is MVDream's approach, where basically every pixel in every image gets to look at itself as well as all the other images. So all the 4 views that we want to generate. Now, MVDream works well. It actually generates pretty good views, but it has some other limitations that basically exist. It cannot generate more than 4 viewpoints. It has these fixed and 4 orthogonal views. And it does not have any inherent 3D bias to maintain consistency. So this happens because since we just repurposed the self-attention that was trained to look at only one view in Stable Diffusion, we took it and we extended it to 4 different views. It creates this front-facing bias, where basically all the 4 generations have these 4 faces that are looking towards you instead of looking on the sides. And this happens because we took a Stable Diffusion that already had front-facing objects everywhere, and we just repurposed it. And we did not push any 3D priors into it. And that's why it has this tendency. And in my CVPR work, SPAD, we basically try to fix some of these issues by introducing some 3D biases and tricks into this architecture. So this was, again, a good collaboration between Snapchat and U of T. And the task here is similar. We basically want to generate many views given only text. But the difference here is that we don't want to constrain these views. So we want to still keep generating these views from many different viewpoints. And these samples are actually some of the generations from SPAD. And I'll talk about how we do this. And as you can see, there are the issues that we saw with MVDream, where it was copying views from different sites. All those do not exist here. So we start with simple MVDream style model. We have basically these dense self-attention layers in our unit, and we attach them together so that they can attend between each other. Every single view gets to look at the other views. But we introduce this trick from epipolar geometry by constraining these pixels about how they look at each other. So from epipolar geometry, we know that each pixel in the source view, which is on the left here, it gets to look like each pixel in the source view subtends an epipolar line on the right view, which is just 2 cameras in the space. And we can use this trick to basically constrain where this pixel will lie in the other images. So in this case, let's say this is our source view, and the source view for this particular pixel, it will only lie along certain lines on the rest of the 3 views that we are interested in. And since we do not want a front-facing bias to occur in this case, we can only constrain this pixel to look at these lines instead of all the pixels in the other images. This basically prevents it from copying their faces or any other attributes other than where the pixel should lie. So this is the first trick. We basically constrain or mask the self-attention along epipolar lines. And epipolar lines can reason about where it should lie, but it cannot reason about the ray direction. And this leads to one problem that I'll talk about next. So for example, consider these 2 images. This is the source pixel, and this is the epipolar line along which it is basically attending. So the issue here is that this epipolar line can be subtended by 2 different cameras that are placed opposite to each other. And we do not know which one of these cameras has created this line. Basically, it has no understanding that if it should terminate here, like if we had the ground truth depth for this object, if it should terminate here or from here, where the camera is in the front or in the back. And there is this issue that it just cannot tell us the redirection, it can only tell us a line. And this leads to this problem of flipped view generation, where we basically are able to generate 4 views, but the left and the right, or the front and the back, one of them gets messed up and gets aligned towards each other. This is different from the front-facing issue, which basically has this problem of everyone looking front. Here, we don't understand the left and the right, or opposite from the front. And to reason about the direction of the camera rays, we basically use Plucker coordinates. Plucker coordinates is this representation of camera ray where basically, if given some world origin and camera center, we take the cross product of the world origin to camera and the ray that is coming out of the camera, and that becomes our O cross D vector, which is a 3 cross 3 vector, and we attach that to the direction of the camera ray. And this becomes a 6-dimensional vector, which basically allows us to reason about this direction of the camera, of which direction the ray is facing, or where it starts and where it ends. And we use these Plucker coordinates as positional encodings. So we basically take these Plucker embeddings and we attach them to our images before the diffusion starts in the attention layer. And now we basically can enable reasoning between the directions in which these camera rays are going. So inspired, we basically made these two changes. We replaced the self-attention mask with an epipolar mask. So we constrained where every pixel can look in the other images. And the second one was inserting Plucker coordinates. And we push these Plucker coordinates through a zero initialized MLP. And what that does is it basically stops, it basically initializes our network as an identity. So we cannot break anything when we start training. And here are some training details for this SPAD model. We trained 4-view models on 16 to 32 H100 GPUs for 100,000 steps. And we had an effective batch size of nearly 1,700 samples. So this is somewhat of a large scale setup still. One thing that we noticed in SPAD was that the quality of the data mattered much more than the quantity, especially because we are fine-tuning and fine-tuning already trained model. And we noticed that even if we dropped our data set size by 75%, we only trained on 25% of our data, we still are able to achieve good or much better results than INVs or 0, 1, 2, 3, or all of those methods. And the way we do this, like the way we do filtering, is actually just automated. We just looked at the metadata and we saw what is the like, view, and comment count on these assets. These assets were crawled from, observers' assets are crawled from some website. They have these metadata. We filter them by the most popular assets, and we get this subset that we can train on. Let's see some quantitative results about this. So we see that SPAD is able to outperform MVDream, and SyncDreamer is another baseline in our setup. And it is able to do this on the view quality and text-to-view alignment both. So we have two metrics here, inception score, which tells us about the quality of the view, the generated view, and the clip score, which tells us about text-to-view alignment, of how much aligned the views are with the input text. There's a quick note here. These numbers only compare quality of generations and text-to-view alignment, and not 3D consistency, which is what we are shooting for with SPAD. We care more about 3D consistency and also about this stuff, but a little less. Like this is just the generation, and we know that Stable Diffusion already does it pretty well. So to quantify how consistent we are in 3D, we can convert our setup into a novel view synthesis task. It is hard to evaluate a 3D consistency of just a text-to-views model because we don't have ground truth. It can generate any of the 3D assets, and we don't know how they look in actual or how consistent they are in 3D. So for this, we basically make a small change. We freeze one of the 4 views to an input view. So basically, let's say out of these 2 views, like if we wanted to generate 2 views out of our model, we will just freeze one of them and let the model denoise only the second of them. And then now that we have a novel view synthesis model, we can use novel view synthesis metrics to compare our method with other baselines, which is INVS and 0, 1, 2, 3. We see that on LPIPs, on perceptual similarity, SPAD is able to outperform all the other methods. So in this case, the lower is the better. It is basically a distance metric. On structural similarity, SPAD again outperforms 0, 1, 2, 3 and INVS, and it is comparable with SyncDreamer, which is shown in green here. And that's also because SyncDreamer has like a much expensive explicit 3D representation in its latent space. So it's much harder to train SyncDreamer than it is to train SPAD, but still we are able to perform comparably with respect to it. And we also perform very well on PSNR, but we lose out to INVS here. And a reason here is that INVS can directly transfer the source pixels into the target view. And that actually gives it an ability to basically remain faithful to small details, but it breaks the bigger things, like basically the structure of the objects and so on. So there is this trade-off. Like using INVS, you can get very good visual quality in terms of PSNR, but not as good of a structural similarity. So here are some more qualitative results. All of these are generated in a single forward pass using SPAD, and they were conditioned on text and poses. So if we are able to generate these views from various viewpoints, a natural question arises, can we not just generate 3D directly from it? And this is what we work towards after this. And one of the methods to do this is to use score distillation sampling, or SDS, where we basically instantiate a representation in 3D, such as a NERF, and we use our method to supervise the reconstruction of an object given this NERF. So we basically sample viewpoints from different places, use our multiview model, piece it together, and create an optimization problem. And we find that works. And here is like just again a visual of that happening. So we generated these assets just from text. However, there is this optimization procedure in SDS which makes it slow. And we wanted to check why can't we literally just like take these images and have something much simpler that can generate a 3D object for us. So what we did is like we took the views that were generated by SPAD and we pushed it from a transformer-based decoder. So this is a transformer-based triplane generator that takes 4 views and just directly reconstructs the 3D asset in this triplane method. So it generates a triplane-based NERF. And then we can directly decode from the triplane network the asset that we want. This particular approach was proposed in a different paper, like in a concurrent work. It's Instant 3D. And some folks at Snapchat trained this text to 3D pipeline, and they took SPAD and tried it out on that. And we see that we were able to generate pretty good assets just from 4 views and this triplane generator. And those visuals are here. And this actually enables this 3D generation very quickly. We are able to generate a single asset only in 30 seconds. So that kind of brings me to the end of the research perspective of the talk, like all the research that I wanted to share. And now I wanted to share some learnings, which basically are like technical things that I learned by working with these large models and how like working, basically seeing how they behave when being fine-tuned on smaller sets of data. So here's like the first lesson that I learned, which is like, when we want to fine-tune large models, the quality of the data matters much more than the quantity of the data. The reason I feel that's true is that Stable Diffusion already understands the world pretty well, and it just needs to be steered to the right task of novel view synthesis. Like this is just like a small section, or like it already understands how to generate 3D assets. We just need to tell it how to do the small tasks that we need to do. And it is very important that for that small task, we have good quality data. An example of this is that 0123 XL. This is like another method. It was trained on 10 times more data and 10 times longer, and it actually performed slightly worse when after this training than its original competitor, which was 0123. And the reason is this, that basically as you scale up the data set, the noise and the randomness in it increases and the learning signal decreases, and just throwing more compute and more data did not actually work. And as I said before, SPAT was trained on much smaller data set, only 25% of observers, and it still outperforms 0123 and these other methods that were trained longer. Another thing is that it's easier to use larger base model and use even lesser data, because they have this capacity, or they have this way of being stirred very quickly, or being able to adapt to new things or new losses very quickly, just with the use of very tiny amounts of data. And an example of this was Instant 3D, the later work that I shared, which switched to SDXL, which is a much bigger model, but it only needed not 10,000 assets and not even 200,000 that I used to train SPAT. Another learning was that too much synthetic data can hurt. So basically, if you use too much of observers, then the observers is a data set that is created by taking things created by artists. And they're not going to be as detailed and as high quality as Lion. So Lion was the data set on which Stable Diffusion was trained. And as we train longer and longer on this, on observers, the model becomes more crude and it forgets its photorealism. One trick to basically fix this issue for us was to just train jointly on Lion and observers, and we found that works well. And then another thing, adapting large models to 3D tasks. In this particular line, I feel there are two things that are important. One is like the input parameterization of a task makes a huge difference. So basically, it is much easier to predict deltas between things than predicting values, predicting absolute values. So a simple example of this, maybe not directly related to these works, but if you want to do human body pose estimation, if you want to see how a person is moving in 3D space, I had this work before Imvs. We had two ways of modeling this. One was to directly predict the absolute pose given the previous pose, or we just predict the deltas. And I always felt that this delta prediction, it was much simpler for the model than directly generating absolute values, which involves copying the previous value and then adding things into it. And this is also being seen with the use of positional encodings, that positional encodings enabled really good performance even in language, in transformers, in 2D image models such as vision transformers, and they play an even larger role as we scale up the dimension and go into 3D. We already saw the effect it had in SPAD when we used plucker coordinates as positional encoding. Okay, so this was about like how to adapt into 3D tasks. I have a few more things to say. This is about if you are given a pre-trained model, how do you want to make changes into it? So avoid adding parameters that disrupt the original computation flow. As I said, they are already pre-trained, they're already very good. So you don't want to disturb too many things. If you have to do this, then it will be easier to initialize them to identity. Like if you have to insert new parameters, initialize them in such a way that they have zero weights and bias on the last layer, and they become an identity. And then use the new parameters, have a larger learning rate on them, such that you can train them much faster compared to the rest of the network. They get adapted much more quickly. I wanted to know if anyone has any questions until this point, because after this, I will talk about some of the reflections of my PhD and like what I've learned and so on. But can I take questions?
Maybe can I start as a question?
Yeah, for sure.
Yeah. First, really nice work. Very, very interesting. I guess maybe you covered this, but I missed it. So I see when you were going through your last stuff, the SPAD stuff, and you were showing the multiple views, I was like, oh yeah, the next step, put this into a NERF, and then you showed those results. But I'm just wondering why not have the diffusion model output the NERF parameters itself? Is that an intrinsically harder problem?
Yeah. So that's actually a good question, because we could do that. We could directly generate a NERF or a 3D space. But the problem is the scalability of this approach. We want the things that we're doing to basically just scale on the data we have, right? And if we directly try to generate an output in the 3D space, it gets restricted by how much compute we have, because this will at max be 256 cross 256 cross 256 cube. And that's much tiny. But if I have an alternate approach where I can generate images, those images could be much higher because they are not 3D. And then I can use these images for supervision. There have been approaches that have also done 3D diffusion, but the main drawback was just the scalability. They do not scale after a certain point, or at least not in today's compute. Yeah.
I guess I'm still confused. So, because I guess for the NERF, the approach that I'm saying, you're saying that you would have to put all the data into the NERF representation first, and then train on the parameters of the NERF. So you're saying that the hard part then is that the data is not intrinsically in that parameterization. It's originally images, so it's easier to train with images, or
no, it's slightly different. So what I'm suggesting is that if we directly want to generate NERF parameters from the diffusion model, then we will have to generate this cube of things, or this whole triplane from the diffusion model, right? And that will have a very high complexity in the output. I have to basically apply diffusion on this cube of parameters, or cube of things, instead of just a 2D grid in case of images. And it's just harder to scale that approach. Here, we can have these images rendered in 512 cross 512, but when we go to the NERF, we can actually only render the NERF in a smaller image size, so 128 cross 128, and we can basically render those 128 patches at a multiple viewpoints and use this supervision. So it's just the scalability. It would we would be able to scale to a very big grid using the diffusion model, if that makes sense.
See, but I guess you have to build in these epic polar constraints to get around the fact, because it would naturally obey these.
Yeah.
So there's, I guess, a trade-off, but okay, but makes sense. Thanks.
Yeah. I that totally makes sense, right? That epipolar constraints that we put into place, they were a hack for not having an actual 3D representation, right? And that totally makes sense.
I wouldn't say hack, but I'm just saying it's like a trade-off. Yeah.
Yeah. Thank you. Thanks for the question.
I see another hand from Aviad.
Yeah. Thanks. Yeah, really great stuff. So I'm wondering, you made this point, which I think is super important, and I find it again and again in my work, which is deltas are easier than absolute values. I think this comes up again and again in many different contexts. But I think in your context, so in the earlier works that you've shown, it looks to be a difficult task to predict a novel view, for example, on the opposite side or at 90 degrees, and you showed some problems with that. But you could think of a case where you don't just go ahead and predict the opposite side, but you kind of slowly rotate the viewpoint, and then you predict delta and another delta and another delta until you reach the opposite side, right? And maybe that case will preserve consistency in line with what you said, that deltas are easier than absolute values.
Actually, we tried that. The only issue with Imvs work was not that the in-painting model was worse. It was just this depth that we have to rely on, because when we unproject into 3D, we start seeing some disturbance in the surface. And if we do this iteratively, that basically accumulates. It will, as you go on in painting more and more things will get blurrier. And if we iteratively use the monocular depth multiple times, then there is this scale ambiguity that we cannot even rescale it to the right size of the object. And that's what prevented us from directly doing that iterative sort of setup. But I do agree, yeah.
Yeah, I mean, you could imagine that you have both constraints, right? You have like the direct, let's just interpolate that, and that will introduce information that's not constantly blurred, and then you can want it to be consistent with the, yeah, you could work your way around the blurring somehow. I just feel like there's something really
Mhm.
true about this observation that deltas are easier. Yeah, really cool
Yeah,
stuff. Thank you, Yash.
yeah. I have one more thought here. So I feel like these deltas are easier because neural networks in general are even bad at just copying their inputs. Like there was this paper, I don't remember when, like I think quite a few years ago, where they tried to do simple arithmetic, which just require like neural networks to copy their inputs. And it was even hard for just dense layers to do that, or just do simple arithmetic. And I feel like that all depends on how fast these input outputs can move. And yeah, and that's why I feel like just predict the deltas, not the absolutes. Yeah.
Thanks.
Thank you.
Any other questions? If not, maybe we can go on. Yeah.
Sure. So just wanted to like say a few words about reflections from my PhD journey so far. I believe this is a very subjective sort of like subjective perspective. Differs from person to person, and differs based on which group they become a part of, and so on. And yeah, so I will just like try to share some bits that I feel like have helped me in my PhD, and just few simple things that I thought were like might generalize beyond the things that I cannot control for. So the first thing I would like to say is like I think I have been somewhat lucky working at Snapchat for a long time because I could use their computer infrastructure, and that basically has led me to feel like I could like basically get access to some resources and some expertise. So yeah, I think I'll have that point ahead in the slide, so I'll just continue and start with it. So the first one is basically how to spend time on right things. I feel like it's important to spend time on choosing the right problems and developing a taste. I have been told not to jump too quickly into problems. This has happened quite a few times in the beginning when I just picked whatever was the coolest thing out there and just tried like working on it, and then I realized, oh, okay, it was just a fluke. So, like, works for one thing, does not work for others. So I feel like talking to my advisors and other folks who were much more experienced has helped me here. Second thing here that I mentioned was about like I got like this opportunity to work at Snapchat for a long time. This happened because I was just continuously reaching out to other folks, and this has led to like great collaborations, better opportunities, and also access to like lots of more GPUs, and much more exposure than what has happened if I've just stayed within my small group, which is like just starting. Like when I joined U of T, my advisor came here at the same time, and we were just starting up, and the exposure got just amplified because I was able to reach out to more and more folks. And some other things were like basically learning from other people. This I think like I was not as involved in like going to my workplace, especially around the pandemic and once the pandemic had settled in, and when things were opening up. But as I started going to lab more often, just grabbing food with my colleagues and like, going to talks and conferences, I felt like my learning curve has shot up quite a bit. I was able to learn much more and so on. And I feel like this has helped a lot. And the last thing that I just want to like reflect back was like just staying updated. We had like a very big Slack channel where like everything was being shared, how different folks did different things, how their tools were optimized, their setups were optimized, and so on. And I felt like all of those things just like led to fast iteration on ideas. And this has helped to avoid some sunk cost, which generally happens, especially in this space today where like things are moving just too fast, and there is like always this fear that like you might get scooped and so on. So Yeah. These were like just few bits that I feel like have been useful to me, especially while doing PhD. I still have another a year and a half to go ahead. So looking forward to having more learnings and reflections of similar kind ahead. Yeah. Just want to say thanks to like all my collaborators. On the left side is my lab, right side are folks from Snapchat. Uh, I have departed from Snapchat. Would be joining another team in Meta soon. But I had an amazing blast for the 1.5 years I spent with them. And yeah, thanks for inviting me. Thanks for listening to me. Thanks so much. Yeah.